One of the most important chemical properties of S-block elements, especially the group 1 alkali metals, is their ability to react rapidly with oxygen. Oxygen is one of the most abundant and reactive gases in Earth's atmosphere. When a freshly cut alkali metal is exposed to air, it immediately comes into contact with oxygen molecules. Because alkali metals have only one loosely held valence electron with the general electronic configurations, they lose this electron very easily. Oxygen atoms readily accept these electrons, causing a chemical reaction in which metal oxides are formed. This reaction is responsible for the rapid loss of the shiny metallic appearance of alkali metals when they are exposed to air. The image summarizes the general reaction as metal plus oxygen metal oxide. This equation represents the basic reaction of alkali metals with oxygen. During the reaction, the metal is oxidized because it loses electrons, while oxygen is reduced because it gains electrons. The product formed is called a metal oxide, which is an ionic compound containing metal ions and oxide ions. The image uses sodium as the main example. The balanced chemical equation shown is 4Na plus O2 NiO. This equation shows that 4 sodium atoms react with 1 oxygen molecule to produce 2 molecules of sodium oxide. During this reaction, every sodium atom loses its single valence electron to become a Na ion, while each oxygen atom gains 2 electrons to become an oxide ion. The attraction between the positively charged sodium ions and negatively charged oxide ions forms the ionic compound sodium oxide. The reaction between sodium and oxygen is highly exothermic, meaning that it releases a large amount of heat. The image clearly mentions that the reaction is highly exothermic. The energy released comes from the formation of strong ionic bonds in sodium oxide. When these new chemical bonds are formed, chemical potential energy is converted into thermal energy, causing the temperature to rise. Because heat is released rapidly, sodium may burn with a bright yellow flame. The yellow color is produced because heated sodium atoms emit yellow light when their excited electrons return to lower energy levels. This characteristic flame color is often used in flame tests to identify sodium compounds. The image also explains that fresh, shiny metal quickly becomes dull due to oxide formation. When sodium is freshly cut, its surface is bright, smooth, and highly reflective because of its metallic luster. However, as soon as oxygen in the air reacts with the surface, a thin layer of sodium oxide forms. This oxide coating scatters light rather than reflecting it uniformly, causing the shiny surface to lose its metallic appearance and become dull gray or whitish. The image illustrates this process by showing a shiny sodium block gradually becoming covered with a white oxide layer as oxygen molecules surround it. This demonstrates how quickly alkali metals react with oxygen under ordinary atmospheric conditions. The sequence shown in the image explains the process clearly. Metal plus oxygen metal oxide protective oxide layer. This means that oxygen reacts with the surface of the metal to produce a layer of oxide. In some metals, this oxide layer acts as a protective coating that prevents further reaction with oxygen. For example, aluminum forms a very thin but tough oxide layer that protects the metal underneath from further corrosion. However, alkali metals behave somewhat differently. Although a thin oxide layer forms initially, it is generally not sufficiently protective because alkali metals are extremely reactive. Cracks or breaks in the oxide layer expose fresh metal to oxygen, allowing the reaction to continue. Consequently, alkali metals continue reacting until much of the metal surface becomes oxidized. The image also presents an important special case involving potassium. Unlike lithium and sodium, potassium can produce 3 different oxygen compounds depending on the amount of oxygen available. The first compound is potassium oxide, whose formula is Co. This compound forms when the oxygen supply is limited. When more oxygen is available, potassium may instead form potassium peroxide, whose formula is Co in this compound, oxygen exists as the peroxide ion instead of the normal oxide ion. Under conditions where oxygen is abundant, potassium can also produce potassium superoxide, whose formula is, Co here, oxygen exists as the superoxide ion. This is an unusual oxygen containing ion that is stable only with highly reactive metals such as potassium, rubidium, and cesium. The image explains this progression as potassium oxide, potassium peroxide, potassium superoxide. This behavior is unique because the heavier alkali metals are reactive enough to stabilize oxygen in these more oxygen-rich forms. The reason potassium can form peroxides and superoxides is directly related to its greater reactivity. Since potassium atoms are larger than sodium atoms, their outermost electron is farther from the nucleus and is held less strongly. Potassium therefore loses its electron more easily, allowing it to react with larger amounts of oxygen and produce compounds containing more oxygen atoms. The image also shows the trend. Lithium, sodium, potassium with an arrow labeled increasing reactivity. This means that the tendency to react with oxygen increases steadily as we move down group 1. Lithium is the least reactive among these three elements. Sodium reacts more readily and potassium reacts even more vigorously. The increasing reactivity occurs because atomic size increases down the group. As each new electron shell is added, the outermost electron moves farther from the nucleus. At the same time, the shielding effect produced by the inner electron shells increases. Together, these factors reduce the attractive force between the nucleus and the valence electron. As nuclear attraction decreases, the outermost electron becomes easier to remove, since the first step in the reaction with oxygen is the loss of this electron. Easier electron removal leads directly to faster and more vigorous reactions. Lithium reacts with oxygen to form mainly lithium oxide. 4Li plus O, 2Li sodium reacts primarily to produce sodium oxide. 4Na plus O, 2NaO. Although sodium oxide is the main product under controlled conditions, sodium can also form sodium peroxide when excess oxygen is available. Potassium reacts even more vigorously and commonly forms potassium superoxide in air because its high reactivity favors the formation of oxygen-rich compounds. Rubidium and cesium, which lie below potassium in group 1, are even more reactive. These heavier alkali metals also readily form superoxides because their very low ionization energies allow electron transfer to occur extremely easily. The formation of oxides explains why alkali metals cannot be stored in open air. The image includes an important warning stating that alkali metals are highly reactive and should be stored under mineral oil or kerosene. These liquids prevent oxygen and moisture from reaching the metal's surface. Without contact with oxygen, oxidation cannot occur, and the shiny metallic appearance is preserved. This storage method also protects the metals from reacting with water vapor in the air. Since alkali metals react rapidly with both oxygen and moisture, exposure to the atmosphere quickly destroys their clean metallic surfaces. It is also important to understand that these reactions are examples of oxidation-reduction reactions. During the reaction, the alkali metal loses electrons and is therefore oxidized, while oxygen gains electrons and is therefore reduced. Electron transfer from the metal to oxygen is the fundamental process responsible for oxide formation. The metal oxides produced are basic oxides because they react with water to produce alkaline hydroxide solutions. For example, NaO plus Ho2NaOH. This reaction produces sodium hydroxide, a strong alkali. Similarly, lithium oxide forms lithium hydroxide, and potassium oxide forms potassium hydroxide. This basic nature of the oxides is another characteristic property of alkali metals. Group 1 alkali metals react rapidly with oxygen because they possess a single loosely held valence electron that is easily removed. During the reaction, the metal loses electrons while oxygen gains electrons. producing metal oxides in highly exothermic reactions. The oxide layer formed causes the shiny metallic surface to become dull. Lithium mainly forms lithium oxide, sodium forms sodium oxide, while potassium, because of its greater reactivity, can form potassium oxide, potassium peroxide, and potassium superoxide depending on the oxygen supply. As atomic size increases down group 1, electron loss becomes easier, causing the reactivity toward oxygen to increase from lithium to sodium to potassium, and continuing to become even greater for rubidium and cesium. This reaction demonstrates the close relationship between atomic structure, electron transfer, and the chemical behavior of the alkali metals. Chemical properties of S-block elements, especially the group 1 alkali metals, is their ability to react rapidly with chlorine gas. Chlorine is a highly reactive non-metal belonging to group 17, also known as the halogens. Because alkali metals easily lose one electron and chlorine atoms readily gain one electron, these two elements react very vigorously with each other. The reaction produces stable ionic compounds called metal chlorides. Among these compounds, the most familiar example is sodium chloride, commonly known as table salt, which is used every day in homes, industries, medicine, and food preservation. The image shows the reaction between sodium metal and chlorine gas. The balanced chemical equation is 2Na plus Cl 2 NaCl. This equation shows that two sodium atoms react with one chlorine molecule to produce two formula units of sodium chloride. Since chlorine exists naturally as a diatomic molecule, two sodium atoms are needed so that each chlorine atom receives one electron. To understand this reaction properly, we must first examine the electronic configurations of the two elements. Sodium has the electronic configuration 2008-1, meaning it has one valence electron in its outermost shell. Chlorine has the electronic configuration 2008-7, meaning it has 7 valence electrons and requires one more electron to complete its octet and achieve the stable electronic configuration of the nearest noble gas, argon. Because sodium wants to lose one electron and chlorine wants to gain one electron, they are perfectly suited for an electron transfer reaction. When sodium and chlorine come into contact, sodium immediately transfers its outermost electron to chlorine. The image clearly illustrates this electron transfer. It shows sodium changing into a Na ion after losing one electron, while chlorine changes into a Cl ion after gaining that electron. This transfer of electrons is the fundamental process responsible for the formation of sodium chloride. The reactions can be represented as two separate half reactions. The oxidation half reaction is Na plus E. Here, sodium loses one electron and becomes a positively charged ion. Since oxidation is defined as the loss of electrons, sodium is oxidized. The reduction half reaction is Cl plus ECl. Here, chlorine gains one electron and becomes a negatively charged chloride ion. Since reduction is defined as the gain of electrons, chlorine is reduced. Because oxidation and reduction occur simultaneously, this reaction is called a redox reaction. After electron transfer occurs, the positively charged sodium ions and negatively charged chloride ions attract each other through strong electrostatic forces. This attraction forms an ionic bond. A compound formed by ionic bonding is called an ionic compound. The image emphasizes that an ionic compound is formed because one electron is transferred from sodium to chlorine. Unlike covalent compounds, where atoms share electrons, ionic compounds are formed by the complete transfer of electrons from one atom to another. The image also shows the formation of the crystal lattice. Sodium chloride does not exist as separate NaCl molecules. Instead, millions of sodium ions and chloride ions arrange themselves into a regular three-dimensional ionic crystal lattice. In this structure, every sodium ion is surrounded by chloride ions, and every chloride ion is surrounded by sodium ions. This arrangement maximizes the attractive forces between opposite charges while minimizing repulsive forces. The formation of this crystal lattice releases a large amount of energy, making the reaction highly exothermic. The image specifically states that the reaction is highly exothermic. During the reaction, chemical potential energy is converted into thermal energy, causing a significant rise in temperature. If sodium metal is placed in chlorine gas, it reacts so vigorously that bright light and heat are produced. The image shows sparks and intense energy being released as sodium reacts with chlorine. This visual representation emphasizes that the reaction occurs very rapidly and releases a considerable amount of heat. The final product shown in the image is sodium chloride. The image identifies several important properties of sodium chloride. First, it is common table salt, the substance used daily for seasoning food and preserving food. Second, it is an ionic compound, consisting of sodium ions and chloride ions held together by strong ionic bonds. Third, it is a white crystalline solid. Sodium chloride forms transparent or white cubic crystals because of its regular ionic lattice structure. Fourth, it is widely used in food and industry. Besides its use in cooking, sodium chloride is essential in chemical manufacturing, water treatment, road de-icing in cold countries, medical saline solutions, and many industrial processes. The image compares the substances before and after the reaction. Before the reaction, sodium exists as a shiny metallic solid while chlorine exists as a greenish-yellow poisonous gas. After the reaction, both dangerous reactants disappear and are converted into a stable white crystalline solid called sodium chloride. This dramatic change demonstrates how chemical reactions can produce substances whose properties are completely different from those of the original reactants. One of the reasons this reaction occurs so readily is the high reactivity of group 1 metals. Sodium has a low first ionization energy because its outermost electron is weakly held by the nucleus. Consequently, sodium loses its electron very easily. Chlorine, on the other hand, has a high electron affinity and strongly attracts an additional electron to complete its outermost shell. The combination of a metal that readily loses electrons and a nonmetal that readily gains electrons makes this reaction extremely favorable. The same type of reaction occurs for all group 1 metals. Lithium reacts with chlorine to form lithium chloride, 2Li plus Cl, 2LiCl. Potassium reacts to form potassium chloride, 2K plus Cl, 2KCl. Rubidium forms rubidium chloride, and cesium forms cesium chloride. These compounds are collectively known as alkali metal chlorides. All are ionic compounds containing M ions and Cl ions. As we move down group 1, the reactivity with chlorine increases because atomic size increases, shielding becomes stronger, and the outermost electron becomes easier to remove. Lithium reacts relatively gently, sodium reacts more vigorously, potassium reacts even more rapidly, while rubidium and cesium react extremely violently with chlorine gas. The image also contains important laboratory safety warnings. Chlorine gas is identified as a toxic gas. It has a yellowish-green color, a strong, irritating smell, and can damage the respiratory system if inhaled. For this reason, chlorine reactions are always performed inside a fume hood or well-ventilated laboratory using appropriate protective equipment. The image also warns that sodium undergoes a vigorous reaction, meaning that considerable heat and light are produced. Therefore, these experiments should only be carried out under controlled laboratory conditions by trained personnel using proper safety precautions. The formation of sodium chloride also demonstrates an important principle known as the octet rule. Sodium loses one electron and achieves the stable electronic configuration of neon, while chlorine gains one electron and achieves the stable electronic configuration of argon. Both ions therefore attain complete outer electron shells, making the ionic compound highly stable. This reaction is also an excellent example of why metals and non-metals often react so strongly with one another. Metals tend to lose electrons and become positive ions, while non-metals tend to gain electrons and become negative ions. The strong electrostatic attraction between these oppositely charged ions produces stable ionic compounds. In summary, Group 1 alkali metals react rapidly with chlorine gas because they possess one loosely held valence electron that is easily transferred to chlorine. During the reaction, sodium loses one electron to become Na, while chlorine gains one electron to become Cl. The resulting oppositely charged ions attract each other strongly, forming the ionic compound sodium chloride according to the balanced equation 2Na plus Cl 2NaCl. The reaction is highly exothermic, releasing large amounts of heat and light. Sodium chloride is a white crystalline ionic solid, commonly known as table salt, and is one of the most widely used chemical compounds in everyday life. Similar reactions occur for all Group 1 metals, producing stable metal chlorides whose formation demonstrates the fundamental principles of electron transfer, ionic bonding, oxidation-reduction reactions, and the relationship between atomic structure and chemical reactivity.